Okay, we've already learned how to use Hess's law to calculate delta H, or enthalpy change, for reactions. Now I'm going to show you a second way, and that's using enthalpies of formation. When we're finished with this lesson, you'll be able to calculate delta H for a variety of reactions in two different ways. First, we'll start with an example. Two forms of carbon. We have graphite and we have diamond. Both of these are made of carbon, pure carbon. The only difference is the arrangement of the atoms. Now we can use the enthalpies of combustion for graphite, which is negative 394 kilojoules per mole, and the enthalpy of formation for diamond, which is negative 396 kilojoules per mole, to calculate the enthalpy change for the conversion of graphite to diamond, shown here, graphite to diamond. The combustion reactions are graphite plus oxygen. When 1 mole of graphite is burned in oxygen, the delta H, or the heat release, is negative 394 kilojoules. When 1 mole of diamond is burned in oxygen, the delta H is negative 396 kilojoules per mole. We can use these two, manipulate them, and find the delta H for changing graphite to diamond, which is the desired reaction we're looking for. So if we actually turn the second reaction around, we'll have diamonds on the right. That'll also give us carbon dioxide on the left, so that will cancel if we turn this around, and it'll give us oxygen on the right, so that oxygen will cancel. When we do that, we'll make sure we have to change our sign here. So that's what I've done down here. The first reaction I've left as is. The second reaction, I just flipped it. Put diamonds and O2 on the right and CO2 on the left. Since I did that, I had to change the sign. Anytime you turn a reaction around, you have to change the sign for the H. Now that we've done this, we can add these two together, and carbon dioxide on the left cancels with carbon dioxide on the right. O2 on the left cancels with O2 on the right. And what we have left is our desired reaction, graphite to diamond. So we sum these two and we get 2 kilojoules. What that tells us is that 2 kilojoules of energy is required to change 1 mole of graphite to diamond. Now this process is endothermic. We know that because this is a positive value. So we've just calculated something that could not be obtained by direct measurement in a calorimeter because the process is much too slow under normal conditions. However, we can calculate that from heats of combustion, as we did in the previous example. We can also do this with heats of formation, standard enthalpies of formation. F, standard enthalpy of formation, that's the symbol for it. What the definition of this is that the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. Now, standard states is has clearly defined conditions that we'll talk about in just a second. But first, let's talk about this little degree sign. Anytime you have a degree sign in a thermodynamic function, that indicates that that process was carried out under standard conditions. Okay, and we just said that the standard state for a substance is a precisely defined reference state. We'll talk about what those are next. So, important points to remember about standard enthalpies of formation. First, the delta HF is always given per mole of a compound. So it'll be given in kilojoules per mole for formation of 1 mole of that compound. Second, delta HF involves formation of a compound from its elements with the substances in their standard states. What are standard states for elements and for compounds? That's number 3. Standard states are defined. For an element, it's the form in which the element exists at 25 degrees Celsius and 1 atmosphere. Usually you can look at the periodic table and the color will give you the state. For a compound, If the compound is a gas, then the standard state is it is at a pressure of 1 atmosphere. If it's a solid or liquid compound, it's the pure solid or liquid. For a substance in solution, it is at a concentration of exactly 1 molar. And lastly, the delta HF for an element in its standard state, such as barium solid or nitrogen gas, equals 0. So if it's an element in its standard state, the state that it would be in at 25 degrees Celsius and 1 atmosphere, then its enthalpy formation equals 0. And let's see if we understand this. All right, which of the following will have standard heats of formation equal to 0? Hydrogen gas, mercury solid, carbon dioxide gas, water liquid, or bromine liquid? I'll give you a minute to think about that. Pause the video if you want to pause it first. Okay, let's think about this. Let's take each one of these. H2 gas. That's an element, and it is in its standard state because at standard conditions, or 25 degrees and 1 atmosphere, hydrogen would be a gas, and it's also diatomic. So yes, hydrogen gas has a standard heat of formation of 0. How about mercury solid? It is an element, but it's in its solid state. What state is mercury normally? Mercury is normally a liquid. So no, that would not have a standard heat of formation of 0. Carbon dioxide gas, is that an element? No. Only elements in their standard state can have a standard heat of formation of 0. That also rules out water because it's a compound. How about bromine liquid? Is bromine a liquid under normal or under standard conditions? Yes. It's a diatomic liquid. So yes, 2 of these would have standard heats of formation of 0. Here are a couple of different reference charts that you would use that give the delta HF or standard enthalpies of formation for several compounds. Notice it gives O2 at 0, H2 0, graphite 0, and you can look at the various other ones. We'll be referring back to these in just a minute. Now, how do you use these? Here's the formula, and it looks pretty complicated, but it's really not as complicated as it looks. All this says is that the enthalpy change for a given reaction, delta H for a given reaction, can be calculated by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. So products minus reactants. What is this? NP and NR? The number of moles of products times their standard enthalpies of formation. The number of moles of reactants times each of their standard enthalpies of formation. The sum of the products minus the sum of the reactants. Remember, the delta HF is given for 1 mole. So if a given reaction has more than 1 mole, you have to multiply the number of moles by that. And also, elements are not included in the calculation, again, because elements have a enthalpy of formation of 0. Start with C3H6. Found it here on this chart, and it tells us that the delta HF is positive 20.9. So I'll go ahead and write that under there, 20.9, and that's kilojoules per mole. We have O2. We should know already that oxygen gas has a standard enthalpy of formation of 0 because it's an element in its standard state. Carbon dioxide, here it is, and it's negative 394 per mole. And then water is right here, negative 286 per mole. Now we tense, and then it's products minus reactants. So we'll start with the products. We have 6 moles of carbon dioxide. So So we're going to say 6 times negative 394 plus, we have 6 waters, so we're going to say 6 times negative 286 and that will give us the enthalpies of formation for our products. I'll just go ahead and write this over here, products. Do the same thing for our reactants. We have 2 moles of C3H6, 2 times positive 20.9 plus we have 9 moles of oxygen, which has a standard enthalpy of formation of 0. If we add those, that'll be for our reactants. And then we're just going to subtract our reactants from our products. So the sum of our products is negative 4080 minus the sum of our reactants, which is positive 41.8. We get a negative 4121.8 kilojoules per mole. Now you can go ahead and pause the video and try this one, then we'll work it out together. Alright, so let's go ahead and write the enthalpies of formation below each one. Na, since it's an element in its standard state, has an enthalpy of formation of 0. Water is given as negative 286 kilojoules per mole. Sodium hydroxide is given as negative 470 kilojoules per mole. And hydrogen is an element at standard state, therefore 0. We have 2 moles of NaOH times negative 470 plus 1 mole of hydrogen times 0, and that's our products. Subtract our reactants from that. We have 2 moles of sodium at 0 plus 2 moles of water at negative 286. And when you do the math, you get negative 368 kilojoules per mole for the enthalpy change for that reaction.